Section 2.2, the inverse of a matrix. You've previously discussed inverse operations throughout math. You've also discussed the inverse of a number. Now, numbers, of course, have an additive inverse and a multiplicative inverse. We're concerned with the multiplicative inverse. If I had, for instance, 7, its multiplicative inverse is the reciprocal 1/7. When I multiply those, I get the multiplicative identity 1. We want to have something similar for a matrix. And some matrices will have an inverse, some will not. So I start off with an n by n matrix A. Very important, only square matrices can have an inverse. A square matrix is said to be invertible if there is another n by n matrix C satisfying that CA is equal to AC is equal to IN. IN, the identity matrix, is the multiplicative identity for matrix multiplication. Now, also in this definition is a fact. Any matrix will commute with its inverse. That is one of the matrices a matrix necessarily would commute with its inverse. Okay. We call C the inverse of A, and we will denote it similar to this as A with a -1 superscript. Fact: if A is invertible, the inverse is actually unique. There's a little proof done here. I'll write it beside it to illustrate it a bit better as I explain. Assume I have two inverses for the matrix A, B and C. And by definition, BA equals the identity matrix, as does CA. Well, we'll start with the matrix B. Well, we know that that matrix is the same as BI. If I multiply B with the identity matrix, that's equivalent to B. But the identity matrix is, in fact, CA, because C is the inverse of A. Now, while matrices don't generally commute, a matrix must commute with its inverse. So CA is the same as AC. Matrix multiplication is not commutative, but it is associative. So I can rewrite this as BA times C. Now this is interesting, because BA, if B is the inverse of A, BA is the identity matrix. And the identity matrix multiplied with any appropriately sized matrix will just give me back that other matrix. So I've worked through here to explain that B must in fact equal C. So by this proof, we can see that in fact the inverse is unique, because I could go through the same chain of logic to prove that for any matrix, it can have only one inverse. So we denote the inverse, as I said, A to the negative first. We have that A inverse is equal to A inverse A, and both products are the n by n identity matrix. Not all n by n matrices are invertible. A matrix which is not invertible is sometimes called a singular matrix. An invertible matrix is called a non-singular matrix, although generally speaking we will use the terms singular to contrast with invertible. So here's a matrix given. This is an invertible matrix, -3, -4, 1, 1. We want to find its inverse. So we know that the product needs to be the 2 by 2 identity matrix. So we start off with a general matrix, A, B, C, D, and we want to find this. So let's think about what the product of these two matrices would be. -3, -4 multiplied with AC. Well, that will be -3A minus 4C. The first row multiplied by the second column will give me -3B minus 4D. The second row multiplied with the first column will give me A plus C, and the second row multiplied with the second column will give me B plus D. Now the idea is these two products are equal. What I just found is the same as the identity matrix, which means -3A minus 4C is equal to 1, and A plus C is equal to 0. Which means then that A is equal to minus C, and I can put that into the first equation to say -3 times -C minus 4C is equal to 1. What does that give us? Well, that gives me positive 3C minus 4C. In other words, -C equals 1, which means C is -1. which means A is positive 1. I can do something very similar for B and D. Now be careful here. In the second column, the top entry is 0. Negative 3b minus 4d equals 0. B plus d is equal to 1. So solving the second equation for B, I get B is equal to 1 minus d. And let's substitute that into the first equation. So I substitute, I can distribute and simplify. I will have negative 3 plus 3d minus 4d is minus d, which this must mean that d is equal to negative 3. And if d is equal to negative 3, b is equal to 1 minus negative 3, or 4. So what I have now is that A inverse is, be very careful of putting these back together, A, B, C, D. So this will be 1, 4, negative 1, negative 3. This is A inverse. And that means that if I were to multiply the given matrix A on either the left or the right, I would get the 2 by 2 identity matrix. Let's check one of those. If I do multiply this, what do I get? I will have negative 3 plus negative 4 times negative 1, that's positive 4. Negative 3 plus 4 is 1. When I multiply the first row with the second column, I will have negative 12 plus 12, which is 0. When I multiply the second row with the first column, I will have 1 minus 1, which is 0. And when I multiply the first row with the second column, I will have 4 minus 3, which is 1. So that is indeed I2. So we do know that this is in fact matrix of A, the inverse of A. We've checked it. All right, theorem. If I have a matrix A, a 2 by 2 matrix A, if AD minus BC is not 0, that condition is sufficient to show that A is invertible, that it has an inverse. Namely, then, the inverse of A is 1 over AD minus BC times D, negative B, negative C, A. What we have done here is along the main diagonal, we have switched and on the anti-diagonal we have negated. If you look at the previous example, you'll see that's what we did, and in fact you can check that AD minus BC for the original matrix A is 1, which is why all we had to do was switch and negate. If AD minus BC is equal to 0, then that is sufficient to say that A is not invertible. So it's sufficient and necessary. A is only invertible if AD minus BC is not equal to 0. Okay, so proof. If A is equal to ABCD, then AA inverse equals the identity matrix implies that AD does not equal BC. So, there's the proof. The proof is not in the key, and I don't remember how to do it. So, I'm just going to move on. The determinant of a 2 by 2 matrix is AD minus BC. The determinant of a 2 by 2 matrix is the product of the entries on the main diagonal minus the product of the entries on the anti-diagonal. So in other words, what we just said is that a matrix is invertible if and only if its determinant is not 0. Now that will be true even for larger matrices, such as 3 by 3 or 4 by 4 matrices, although finding the determinant of a larger matrix is more complicated than this little formula. So we're asked here to find the inverse of this matrix. So we first off check AD minus BC. And we can see that this is in fact not 0, so we're good. This is 32 minus 30, or 2. So the inverse then will be 1 over 2. On the main diagonal, I will switch, and on the anti-diagonal, I will negate. And then I can distribute this to write 2, negative 3, negative 5 halves, 4. And you can check that that will indeed give you the identity matrix when you multiply them, that this is indeed the inverse of the given matrix. One of the reasons that invertible matrices are useful is this gives us an alternate way. If I have an invertible coefficient matrix, I have an alternate means of solving a system. If A is an invertible n by n matrix, then for each B in Rn, the equation Ax equals B has the unique solution x equals A inverse B. How can I prove this? Well, again, rather than filling in the blanks, I'll write it over here. If A is invertible, I can multiply on the left of both sides of this equation A inverse A is the identity matrix. So what I actually get is that X is A inverse times B. So if I have an invertible matrix, this gives me a much easier way of solving a system than row reducing, or even arguably doing linear combination or elimination methods from Algebra 1. So we're asked to use the inverse found in example 2 to solve the system. So this system right here is 8, 6, 5, 4, x equals 2, negative 1. So the inverse we found was 2, negative 3, negative 5 halves 4. So what this is telling me is x is equal to 2, negative 3, negative 5 halves 4. What do I get when I multiply this? 2, negative 3 times 2, negative 1, that will give me 4 plus 3, which is 7. Negative 5 halves times 2 is negative 5. 4, negative 1, that's negative 9. So the solution appears to be 7 and negative 9, which if you check, I would have 56 minus 54, which is 2. I would have 35 minus 36, which is negative 1. So that is indeed the solution of this system. If I have an invertible matrix, A inverse is invertible and its inverse is A. If A and B are both invertible matrices, then so is their product, and the inverse of AB is the product of the inverses of A and B in the reverse order. If A is an invertible matrix, then so is its transpose, and the inverse of A transpose is the transpose of A inverse. So these are just interesting properties that we can use depending on what we need at a given time. So there's some exercises here to find these things. I'm not going to do these. Just be careful when you're doing them. The next bit here deals with elementary matrices. Now you do need to know this term. An elementary matrix is one that is obtained by performing a single elementary row operation on an identity matrix. For example, this first matrix is obtained by swapping rows 1 and 3. This second matrix is obtained by adding twice row 1 to row 2 to replace row 2. And this third matrix is obtained by scaling row 2. Now the significance of these matrices is if I were to take an appropriately sized matrix and multiply it on the left-hand side by one of these matrices, well, multiplying by this matrix would in fact swap the third and first row. Multiplying by this matrix would produce a result which adds twice the first row to the second row. Multiplying by this matrix would scale the second row by a factor of 7. That's the significance of elementary matrices. Now since row operations are all reversible, the swapping of rows, adding a multiple of one row to another, or scaling a row, elementary matrices are also invertible. To determine the inverse of an elementary matrix E, determine the elementary row operation needed to transform E back into the identity matrix, and apply this operation to I to find the inverse. If an elementary row operation is performed on an m by m matrix A, the resulting matrix can be written as EA, where the m by m matrix E is created by performing the same row operation on IM. For example, the matrix 1, 0, 0, negative 3 is an elementary matrix that was found by multiplying the second row by negative 3. Its inverse is found by applying the inverse row operation, that is, multiplying the second row by the reciprocal, negative 1/3. So the inverse of this matrix is 1, 0, 0, negative 1/3. You can check by multiplying that the product of these two matrices will in fact be the 2 by 2 identity. 1, 0 multiplied with 1, 0 gives me 1. 1, 0 multiplied with 0, negative 1/3 gives me 0. 0, negative 3 multiplied with 1, 0 gives me 0. And 0, negative 3 multiplied with 0, negative 1/3 will in fact give me 1. So down here, we're asked to find the inverses of the previously given elementary matrices. Well, as we said, we start with the identity matrix, in this case the 3 by 3 identity matrix for each of these, and I try to reverse the operations. So to reverse this, to get this back to being the identity matrix, I would swap rows 1 and 3 again. So over here, I will do the same thing. I swap row 1 and row 3, and I will end up with I3. Here, if I swap rows 1 and row 3, what do I end up with? Well, I actually end up with that same matrix. So this is possible, but this is the somewhat unusual occasion of a matrix being its own inverse. How about here? Well, what would I do to change this back to the identity matrix? I would use this 1 to clear out this 2. So negative 2 row 1 would be added to row 2. If I did that to the 3 by 3 identity matrix, what would I get? I would have 1, 0, 0, negative 2, 1, 0, 0, 0, 1. Here I scale the matrix, I scale the second row by 7. So to get this back to the identity matrix, I would scale the second row by 1/7. So the inverse then will end up being 1, 0, 0, scaling the identity by 1/7, scaling the second row of the identity by 1/7, would give me this. So there I have all of my inverses. Now, elementary matrices, you can actually once you understand what the row operation is representing, it's fairly simple to determine the inverse. A row swap, I don't need to change anything, I'll just swap the rows back. Adding a multiple of a row to another row, well, I will instead subtract that multiple, so I just change the sign. Scaling a row, I multiply instead by the reciprocal. Now, all of this is useful because if you think about it, if you dig a little deeper, this gives us a way of finding an inverse for an arbitrary matrix. Specifically, a 3 by 3 matrix is what we want to look at. The inverse of E is the elementary matrix of the same type that transforms E back into I. If I have an n by n matrix A that is invertible, it's invertible if and only if A is row equivalent to the identity matrix. And in this case, any sequence of elementary row operations that reduces A to the identity matrix also transforms the identity matrix into A inverse. This goes back to the elementary row operations we were just talking about and saying if we started with the identity matrix, whatever I do to turn this back to the identity matrix, if I start with the identity matrix and do the same thing, I will produce the inverse. So this is going to give us a method for finding the inverse of a matrix. Now this first example is in your notes. This is how you would find the inverse of a 2 by 2 matrix using this method. You should not find the inverse of a 2 by 2 matrix using this method. The method I'm going to show you is intended to find the inverse of a larger matrix. For a 2 by 2 matrix, you should still use the shorter method of finding the determinant negative 3 minus negative 4, which is 1, switching along the main diagonal, negating along the anti-diagonal, and this is in fact the inverse of this matrix. The method I'm about to show you would work for that, but I am telling you, you should really just stick to this. So let's learn this method of finding the inverse of a 3 by 3. You could do it also for 4 by 4, but we probably won't do any examples like that. How do we find the inverse of a 3 by 3 matrix? If you look at the description here, the idea is we want to augment the matrix with the appropriately sized identity. And our goal will be to use row operations to transform this so that I have the identity matrix on the left-hand side. And in that process, I will create the inverse of A on the right-hand side. So, how would I do this? My first step would be to turn this 2 into a 1. So 1/2 row 1 becomes row 1. So I'll have 1, 0, 0, 1/2, 0, 0. Everything else is still the same. Then I would use this pivot to clear out the negative 3. So 3 row 1 will be added to row 2. Now obviously this process can get very messy. This is a nice first example because it's fairly simple. What would I do from here? Well, I would go ahead and swap the next 2 rows. If I swap rows 2 and 3, then I will in fact reach the identity matrix on the left-hand side. So swap rows 2 and row 3. What does that give me? First row is the same, but I'm swapping rows 2 and 3. So our contention is that this is in fact the inverse of the matrix I started with. And you can check. It takes some work, but you can check. Now I'm multiplying 2 3 by 3 matrices, so my product will be 3 by 3 as I expect. So when I do this, 2 0 0 multiplied with 1/2 0 3 2 3 halves, will just give me 2 times 1/2 or 1. 2 0 0 multiplied with 0 0 1 will give me 0. 2 0 0 multiplied with 0 1 0 also gives me 0. Now on to the second row. Negative 3 0 1 multiplied with 1/2 0 3 halves will give me negative 3 halves plus 3 halves, which is 0. Negative 3 0 1 multiplied with 0 0 1 will give me 0 0 plus 1. The second row multiplied with the third column will give me 0 plus 0 plus 0. On to the third row. 0 1 0 multiplied with the first column is going to give me 0. Multiplied with the second column will give me 0. And 0 1 0 multiplied with 0 1 0 will give me 1. So I do in fact have I3. I can also check in the other direction, but let's just assume that that is correct. Now the order of your multiplication is important. You cannot forget that. Matrix multiplication is not commutative. This is one of the essential parts of math that we need to understand. Commutativity is not a given, and matrix multiplication is the most important example of that. Suppose I have some matrices A, B, C, and D that are invertible n by n matrices, and A is equal to B times D minus In times C. We want to solve for D in terms of A, B, C, and I. Well, the idea is I need to solve for D, which means I need to get this by itself. I need to get rid of the matrices B and C. Now, of course, if these were constants, I could divide. There is no division of matrices. So what I would have to do is multiply by matrix inverses. So I multiply on the left by B inverse. B inverse multiplied with itself is the identity matrix. So I can now disregard that. I also need to get rid of C, so I multiply on the right by C inverse. C multiplied with C inverse will also be the n by n identity matrix. So what does this tell us? B inverse A C inverse is equal to D minus I n. We were asked to solve for D in terms of A, B, C, and the identity matrix. Well, we can do that now. D must equal B inverse A C inverse plus the n by n identity matrix. And we have now accomplished the task that was set forth with us. I hope this has helped. I encourage you very strongly to practice with finding the inverse of a 3 by 3 matrix and that quick algorithm to find the inverse of a 2 by 2 matrix and understand where we are going to use these.